In this example, we're given a waveform for the current as a function of time, and we're asked to write down a formula or an equation that describes the current as a function of time, and then also to compute this value at a time of 4 milliseconds. We're also given the fact that the frequency at which this waveform is oscillating is 60 hertz. First thing that we should realize is that this waveform is not such that at time t equal to 0 the current is 0. It's actually shifted. So we look at this picture and we realize, well, this is where a sine wave would start and then continue, and so it's actually shifted to the right, similar to the picture that we had before. Now this is voltage, but remember that in terms of the sine functions, what we're describing for voltage and current are basically the same thing, so we can kind of interchange those ideas. So here the current is shifted to the right. And in our form for the sine wave, we have to know what the angular frequency is. So we can start by calculating the angular frequency from the frequency of 60 hertz. So 2 pi times the frequency, or 2 pi times 60, gives me 377 radians per second. Now in my picture, I see that this is shifted by 120 degrees to the right, so that means that my phase angle is going to be a negative value of 120 degrees. So if I write down my formula for the current as a function of time, it has some maximum value times sine omega t minus the phase angle. Our maximum current is 2 amps. So this is 2 amps times sine of the angular frequency of 377 times the time minus 120 degrees. It's usually a good idea to have some idea what the period is as well, so that we can look at our picture and see if our results actually make sense. So we could calculate the period because we know the frequency. So the period is 1 over 60 hertz, which is 0.016667 seconds, or 16.7 milliseconds. So what that means is that when we're asked to calculate the current at a time of 4 milliseconds from the start, the current has not even gone through one complete cycle yet. It's actually gone through about a quarter of a cycle when we look at the current at that particular time. So if we're going to determine what the current is at that particular time, we have to be very careful with our units, because the angular frequency has units of radians per second, which means that when we plug in for the time here, we have to make sure that seconds are going to cancel with seconds, so our time should be in seconds, not milliseconds. And then also, when we plug in our value for the time and we get a number here, that number is going to actually be radians. So we have radians and we have degrees, so we have to make sure that we're careful and that we are consistent with our units. So we're going to have to do some type of conversion here. So the first thing I'm going to do is I'm going to go ahead and I'm going to say that my time that I'm interested in of 4 milliseconds is actually 0.004 seconds. So I'm going to put that value in. I'm going to multiply some numbers together, and I end up with the current at time of 4 milliseconds, or 0.004 seconds, is 2 amps times sine of, I end up getting 1.508 radians when I multiply these together, minus 120 degrees. So I have to make a decision. I have to decide whether I'm going to use radians or I'm going to use degrees. I can't use both when I'm plugging into my calculator. So for this example, I'm going to convert radians to degrees, and I'm going to make sure that I have my calculator in this particular case set for degrees. So the way that I do that conversion is I realize that 2 pi radians is equal to 360 degrees, so I can set up my conversion where I have 1.508 radians. I can multiply it by 1, which is this ratio of 2 units that are exactly equal, so I put the 2 pi on the bottom to cancel out the radians, 360 on the top, and I end up getting 86.4 degrees. So I can go back into my formula for the current. I can replace the 1.508 radians with 86.4 degrees. I can now subtract those values. I have something in degrees, so I can take sine, I can plug in negative 33.6, multiply by 2, and I end up getting a current of negative 1.18 amps. Let's kind of see if that makes sense over here. So if I were to try to look at one complete cycle, I realize that that's what's shown here, is one complete cycle. So a time of 4 milliseconds is actually smaller than a quarter of a cycle. It's kind of hard to tell, but probably half of the cycle would be somewhere in here, and a quarter would probably be, somewhere, in this range right here. And so, or possibly, I guess, right in here. So I am getting a value that makes sense. It should be negative. It's going to be in this range over here. And so it's a good idea just to have some idea of what you expect to have so that when you get your number, you can say, does it actually make sense? All right, so here we have another example of a waveform. It's a current as a function of time. It's asking us exactly the same question. We have the same frequency. That we want to know what the current is at 4 milliseconds. So we have the same angular frequency. The problem is that the angle that they give us here of 50 degrees, we have to just look at our picture and decide, is this actually a sine function that has been shifted by 50 degrees? And the answer to that is no, it's not. So if I look at where that line hits, it actually hits the maximum of that waveform and not the zero value. So I need to think about how I would have to draw this waveform in order to figure out where the zero would be on the sine function. So I realize that I could draw that waveform going back until it hits the zero axis, and now I look like I have a sine function. And so it's actually hitting someplace over on the left of the zero axis. And of course, I know the distance between the zero part, the zero, time t equal to 0, out here to the maximum is 50. So I have to think about what is this angle in here, which is actually how it shifted to the left. And what I realize is that here's my 0, and when I get to the maximum of a sine function, I've gone through 90 degrees. So the distance between, or the angle, I guess I should say, between the 0 point and where I have measured to 50, that angle is 90 degrees, which means that the angle that this waveform is shifted to the left to go to 0 is actually 40 degrees. In other words, this 40 degrees plus this 50 degrees is giving me the 90. So sometimes in your pictures, you'll be given an angle, but you have to really think about whether or not that's the angle that you would use in your formula, and you have to think about how this is shifted. So this is actually shifted to the left, as in our picture from before, and our angle is 40 degrees. So I'm going to have a positive phase angle, and it's going to be 40 degrees. So I can go ahead and I can plug in. I know the current is the maximum times sine omega t plus the phase angle. So of course, my angular frequency is still 377, and my phase angle here is 40 degrees. Now I'm interested again in knowing what is the current at a time of 4 milliseconds. I have to have everything in seconds for my units to work out. So as with before, I plug in that time of 0.004 seconds. I'm still going to get 1.508 radians because I have the same angular frequency and it's the same time that I'm interested in. But I do have a different phase angle here. This is now positive 40. So just to show you that you can do this in terms of degrees or radians, I realized that I can't have radians and degrees in my sine function, so I have to either pick radians or I have to pick degrees. Well, suppose I decided to pick radians here. So I'd have to convert that 40 degrees into radians. So I start off with my 40 degrees, and I can multiply it by 1, which is the same thing as the ratio of the conversions, right? So I know that 2 pi radians is the same as 360 degrees. I need the 360 on the bottom to cancel out the degrees, and I end up getting that 40 degrees is equivalent to 0.698 radians. So I can substitute in 40 degrees, 0.698 radians. I can add those values together. I now have to make sure that my calculator is in radians and not degrees, and I can plug in 2 times sine of 2.206 radians, and I end up getting 1.61 amps. And so again, 4 milliseconds is like a quarter of a cycle, and so it's going to make sense because it's going to be somewhere over in here. So 1 complete cycle, of course, is this whole thing. Halfway is somewhere over here, and then a quarter is somewhere over here. So that value of 1.61 is probably someplace over here, which makes sense.